Here is the MIL-1275 board in action. I've got my power supply, oscilloscope, 15 ohm load, and obviously the board hooked up. So this board is configured for 2.5 amp output. The design can handle 5 amps. That's what we originally designed it to. It can do it. If you need it to go above 2.5 amps, let us know. The problem was the FETs got extremely hot. Even with heat sinks, they got very hot. I think the RDS on of these FETs is around 86, something like that. It's very difficult to get high power FETs with a lower RDS on that would actually fit on the board. I mean, they start to get very large. So it also has a limit. 34.5 volt is the upper limit of this device. So it starts limiting at when it hits that 34.5 volt. Now there's voltage drop across the FETs which affect this. So in reality it's around 35 volts, a little over, is where it starts shutting off. So the operation is this. MIL-1275 is a specific surge specification. It is designed for the 28 to 38 volt bus that the military vehicles use. The spike can be up to 100 volts for 50 milliseconds. I will share this chart graph. I'll put a screenshot of it in the video. So for 100 volts, 50 milliseconds long. Then it ramps down to normal operating voltage over the course of another 450 milliseconds. Right now, I'm just concerned about the 100 volt spike. And actually, I'm not even going to run this at 100 volts because the spec is designed, the board is designed to handle this spike, a 50 millisecond long spike. If I turn the power supply up to 100 volts and just leave it sit, some damage may occur because there is there's some parts on the board that are protected by a 58 volt TVS diode. So extended periods of time is something, 100 volts at an extended period of time is way outside of the mil spec, and you'll damage the board. So I don't want to damage the board here. So what we're going to do is we're going to turn it on. We're going to go 28 volts, enter, turn it on, and we can see, bam, it comes up to 28 volts. The scope is, I think the scope measurement mode is in peak, so it's not going to be an actual RMS value. Okay, so 28 volts, you can see things are working great. FETs are cool. It's 1.87 amps going through it. Things are going great. As it goes above that limit, that upper limit, what's going to happen is for a certain period of time set by a capacitor on the board, a timer capacitor, it's going to allow those FETs to operate. It's going to go up. You're going to see the graph or the oscilloscope go up to the upper limit, and then it's going to shut down. And that length of time that it's on in the upper limit is controlled by that timer capacitor. So to make it easy, we're going to go to 40 volts, and we're going to see 40 volts is this line right here, and you will see that it will not go to it. Bam. So it goes up to the 35 volt range, and then it shuts down. And you can see that it is, what it's doing, it's pulsing back on. This is a cool down period for the FET. Controlled again by the timer capacitor. One thing about this particular circuit, we don't have any control over. It's the analog devices IC. There's multiple time events in this operation. Unfortunately, it's all controlled by one timer capacitor. So the overvoltage time, the cool down time, the overcurrent time, it's all controlled by the same capacitor. Okay, so what we're going to see here, we're going to stop this. Bam. So we're going to see that for this particular capacitor, we're going to zoom in here on this. I'm sorry. I am always confused with this scope. I love this scope, but I always seem to be confused as the buttons. Okay, so, all right, and we're going to go to cursor. I'm sorry, cursor again. Set this cursor here, set this one here, and at 40 volts, our delta time is 422 milliseconds roughly. So it's on for 422 milliseconds. And what that means is for 422 milliseconds, your device is being powered normally through the overvoltage event of 40 volts. So in this sense, it is an uninterrupted MIL-1275 power supply. If the event lasts longer than 422 milliseconds, it will shut down, thereby making it a interrupted MIL-1275. But again, something like this is outside of the MIL spec. If your voltage is, if your bus is running at 40 volts, you got problems, and it requires somebody looking into that, because you got serious problems if your bus is at 40 volts for an extended period of time. Anyway, so we're going to run this again so we can see that this thing is actually, we go back to 28 volts and you'll see that it, after it times out, there it goes back to 28 volts. So things are working great. It's doing what it's supposed to do. And again, back, it resets itself. Now the overcurrent, let me see here. Where am I going to do this here? Yeah, overcurrent. We're going to take out the load and we're going to short it. Bam. And you'll see that it shuts down. It shuts down immediately, protecting the load, which is great. If I were to go to over 2.5 amps on the load, you'll see that timer function start again. I'll put graphs of that on the video. You know what? I take that back. Let me do that right now. Okay, I'm back. Sorry about that. I had to get another load resistor to put in parallel here to simulate, obviously, an overcurrent. And you'll see here, same thing. And you'll see, oh, boop, it spikes. I didn't mean to say boop like bingo there, but let's see here. There we go. Yep. I guess as bingo would say, boop. There. And you'll see it's trying to, it's looking at that load again and trying to turn back on, and it says nope, still way too much current, shut down. And that again is controlled by that timer capacitor. So we get this out, we go back to normal load, and boom, right back. So everything is working very nicely. I'm sorry, I had a little short there. Get rid of that thing. Let's see, undervoltage, we'll go to 11 volts. Enter, you'll see that it shuts down. It's set for 11.3. I think with the FET drop, it's around 11.7 or something like that. There's actually hysteresis. That's unintentional hysteresis. So it'll shut down at roughly 11.7, but it won't turn back on until around 13. So we have to be careful when I'm doing this. So let's go to 12, enter. So 12, and then we're just going to start rolling this down. I believe there we go, 11.9 on this particular circuit. Could be, resistor divider, tolerances and whatnot involved there. But it does what it's supposed to do. And then we go back to 28, and there it goes again. So that's the functionality of it. I will put more in the data sheet for the device. I'll add some of these graphs to the device. I'm sorry, to the data sheet. And I believe that's it. Let me know if you have any questions. Thank you.